So in lecture 2.3, we're going to continue our exploration of computational Boolean algebra and continue our study of the cofactors as important objects for manipulating interesting Boolean objects. In the last lecture, we talked about the Boolean difference. Now we're going to put the cofactors together in another couple of interesting ways and build two new extraordinarily important operations, which are called quantification. They have interesting, unusual names: existential quantification and universal quantification. So it sounds like philosophy, but it's actually an interesting engineering. It's an incredibly powerful and important way of taking complicated Boolean questions, removing the variables that I don't really care about, creating a smaller Boolean object, which we can then interrogate and ask the engineering question that we seek an answer to. So let's start talking about the quantification operators.
This is lecture 2.3. We're continuing our study of computational Boolean algebra. Now we're going to combine the Shannon cofactors in yet more interesting ways to yield some things called quantification operators. So you know that the Shannon expansion lets you take Boolean functions apart and put them together in interesting ways using the Shannon cofactors. Combinations of cofactors do interesting things. We just introduced one, right? The Boolean difference, which was based on the exclusive OR of cofactors. Now we're going to look at other combinations of cofactors. We're going to look at the big ones are these things called the quantification operators. And once I've gotten the quantification operators defined for you, we're going to apply them. We're going to actually be able to do something really impressive. That's the next lecture. So what happens if I just take the two Shannon cofactors, the positive cofactor with respect to variable xi, the negative cofactor with respect to variable xi, and I just AND them together. And this little diagram over here shows exactly what we're doing. We're just, the hardware sort of a diagram. We've got 0 going in over there, right? So that's the negative cofactor. We've got 1 going in the bottom. That's the positive cofactor. All of the other inputs are shared and connected. We've got an AND gate. What do you get? You get something with a very strange name. All right, so we get something called the universal quantification of f with respect to variable xi. And this thing over here, I'm going to write it over here, that's the name of this function. So the upside down a with an x in this case, and f, and then we're going to put parentheses around it, and it reads for all x f. For all x f. So for all xf is a new function. And yeah, that for all sign is actually a symbol from logic, from predicate calculus, if you've ever done that. And just like everything with cofactors, it doesn't have an xi in it. It's a very interesting new function. Sort of the same thing happens. What if I have function f and I OR the cofactors together? Right, so positive cofactor and negative cofactor. Right, I OR them together. I get an interesting new function with another strange name. Backwards e, there exists x f. That is the name of this function. The backwards e is read there exists x f. Right? So the existential quantification is what you get when you OR these things together. And the backwards e sign, the there exists sign, is also from logic. And like everything involving cofactors, both of these functions do not depend on the variable that we just got rid of. In this case, the variable we quantified away. So for all xf and there exists xf, both omit that variable. So these things look really strange, I've got to admit. All right, so let's go back to the hardware diagram because I find that the hardware diagram almost always helps. So let's look at the universal quantification, right? So that's this guy right here, okay? I AND together the negative and the positive cofactors, and let's ask the question, what makes that thing a 1? Because this thing is a function. It's a function of all of the original variables except x, right? What has to be true if this thing is a 1? All right, well, what has to be true, okay, is that these other inputs make the original value of the function f equal 1 for all values of x. That's why it's called for all xf. If for all xf is a 1, for those other variables in the function, then it must have been the case that when you put that pattern of inputs on the original function made a 1 for all values of x, in this case for both values of x, right? Well, what about this one, right? And you know, there exists x, f. What makes that guy a 1? Well, it's, you know, sort of the same thing, right? It must be the case that there exists a value of x that makes the original function equal to 1 for this input pattern of the other variables. Right, so if you look at the and, you know, I mean, obviously both of those things got to have a 1 going into them in order to make the and a 1, so it must be the case that f was 1 for all values of x. But for the OR gate, you know, you only need one of them to be a 1, right? I mean, if both of them are a 1, that's great, but you only need one of them to be a 1. So it must be the case that there exists a value of x that makes at least one of these blocks 1. Might make both of them 1, but it can't be the case that it makes neither of them a 1. That's why it's called there exists. And just like the other cofactor kinds of things, you can do it with respect to more than one variable. So if you quantify away two variables, either universally or existentially, right? And what that really means is that, you know, in this case, let's say you quantify away the y and then you quantify away the x. All that happens is you and together all the cofactors, and for the existential version, all that happens is you OR together all the cofactors. So just like when we took the Shannon cofactor expansion and we decomposed the function into pieces to build the function, and we had 4 cofactors, right? Again, we've got the 4 cofactors. Either you AND them all together or you OR them all together. And again, remember, can't keep emphasizing this enough, these are all functions. They're not numbers. Right, and they're all functions, but they don't have x's in them, which is very strange, because they've got x's written all over them, but there's no x's inside the function. The x's are removed because of the cofactor operation. We got rid of the x, and we made 3 new functions. You can do interesting things with these things, and I'm just going to show you one little example here, and then a much longer example in the next lecture. Consider this circuit. So this is just a little adder circuit. It adds a number A0, A1, A1, A0 to a number B1, B0. And in this case, it really adds a 1-bit number, okay? A 1-bit number, x equals 0 or x equals 1, because we've got the high input for the B bit just pinned to a 0. So this takes a 2-bit number, A1, A0, and it adds a 1-bit number, x. And there's also over here a carry in and a carry out. Right, so the carry in is called D, the carry out is called C. This thing adds a 1-bit number x with possibly a carry in. And so we can ask a question, what if we quantify away the A operand? What if we universally quantify away the A operands? Well, then the A's are going to go away, and this is going to be a function that's only depending on the x number and the D carry in. What is this? It's a function of x and d. It makes a 1 for values of x and d that make the carry, c equals 1, for all values of the operand a1, a0. Right? So this universally quantified function makes a 1 just if you can tell me when there's a carry by only telling me x and d. I don't need to know about a1 and a0. Right? If you tell me these particular values of x and d, I guarantee you that I'll make a carry out independent, okay? Right? The other way to write this is independent. My very bad handwriting. Independent of a1 and a0. What about the existential quantification? Well, same kind of idea. This is also a function of just x and d. It makes a 1 for values of x and d that make a carry out for some value of a1 and a0. And so what just this says is there exists a value of a1 and a0 that will make the carry out 1 if you tell me this x and d. I don't know what it is, and that's a little strange, right? What this function says is if this existentially quantified function makes a 1, all right, if this guy makes a 1, for this value in x and d, then it is true that you can find a value of a1 and a0 that will make it work. It will make, but I don't know what it is. And what's interesting is that we can just go do the math, and we can convince ourselves that this all works. So here is the function for the carry out, right? That's this guy over here, right? It just goes, I'm going to write it over there. There it is. Write A1, A0, X plus A1 and A0 plus X and D. And remember that C with those subscripts just means I'm going to set A1 and A0 to 1, 1, 0, 1, 1, 0, and 0, 0 respectively. So if I set A1 and A0 to 1 and then evaluate the Shannon cofactor, right, well, I'm going to get an X, right, because the A0 and the A1 go away, and then I'm going to get a D. Right, so if A1 and A0 are 1 and I evaluate C, that's what I get. For this one and for this one, okay, what you can see is that if you make A1 a 0, the whole function just goes away. Can't do anything. And if you make A1 a 1 and A0 a 0, it turns out that, again, the first term goes away and the second term is reduced to X and D. And the thing to remember is that when you universally quantify it, basically what you do is you AND everything together. So if you AND all of these things together, well, hey, there's some zeros in there. You're going to get a 0. And that makes sense, right? So the universal quantification says, can you tell me when the carry is a 1 just by telling me X and D, independent of telling me the values of the A operand? And the answer is no, you can't tell me that. There's no way you can tell me that. I have to know the A values to tell me the carry. There's no way you can tell me the low order bit X and the carry in and tell me the high order carry out. It's impossible. Or arithmetically it's impossible. Hey, the Boolean algebra tells me that. What about the existential quantification? Well, for that one, you OR them all together, and for those, the zeros don't really hurt. You're going to get X plus D plus 0 plus XD plus 0, and if you just do the Boolean algebra on that, you're going to get X plus D. Oh, that makes sense. Can you tell me that there is a way to make the carry out a 1 if I tell you X and D? It doesn't need to be true for all values of the A operand. Can you just tell me that there is a value of the A operand that will make this work? Yes, I can. What has to be true? Oh, at least one of the low order bit and the carry in have got to be a 1. If at least the low order bit and or the carry in is a 1, then yeah, there's a way of making the A operand propagate that carry out. Oh, look, the arithmetic works, but I did it all entirely in the Boolean domain. That's what's very cool here.